much for taking the time on a beautiful sunny day to the Characterization at UBC seminar series. I'll introduce our speaker very shortly, but I have a few pieces. The session is being recorded and broadcast to mostly colleagues in the Okanagan. If you haven't joined our mailing list, please join our mailing list. It helps us broadcast to people, but also track who's we're engaging with as part of the cluster of those pieces. And so this enables me to kick us off. Of course, we are today joining from the unceded and traditional territory of the Musqueam people. Always interesting with regards to thinking about how we learn about the world around us, and especially important, as I imagine, when we're starting to look at bioproducts and thinking about the history of the Musqueam people and their relationship to forests and materials in this. It's a great pleasure to introduce my colleague, Dr. Emily Cranston, who's a professor in the Department of Chemical and Biological Engineering and Wood Sciences, so spans across two faculties, and holds the President's Excellence Chair in Forest Bioproducts. Dr. Cranston has very kindly agreed to give us a crash course and some other activities with regards to atomic force microscopy and how we can use this to probe the properties of the materials at the scale. So thank you very much.
Excellent. Thank you so much, Ben. Thanks for the invitation. It's great to be here, and good afternoon, everyone. Thanks for joining. I'm really excited to tell you about AFM today, atomic force microscopy, and sort of going beyond using this as an imaging tool, but to think about how we can measure forces and friction. Because the AFM is pretty unique in that we actually are making physical contact with our samples. So it means there's a lot of information that we can learn. And so today I'm going to give you snapshots of a bunch of different research areas that have really used the AFM in some of these more advanced modes. We'll see how the timing goes, but I've got a few listed up there, looking at ionic liquids as lubricants, surfactants to modify emulsion and latex properties, and then looking at some multi-layered biopolymer packaging. And some of this is ongoing work. Some of it is work from earlier on in my career. And as Ben told you, I am part of both chemical and biological engineering and wood science here. And so the AFM is in the basement of the forestry building if you ever want to come by and see it. So the fact that we have this whole seminar series dedicated to characterization and that you showed up today tells me that you think characterization is important, correct? Yeah. I love characterization. I always think there's more characterization to do, and some of my students have joined today, so they can tell you that that's true as well. So since the very beginning of research, that's really what got me excited about materials, was the characterization and learning new methods. And so while we might all agree that characterization is important, we might have different reasons to do it. And so one way to get at that is to fill in the blank here and see if we have different answers. So I would say you can't blank what you can't measure or what you can't quantify. Characterization isn't always quantitative, but often it is. So we're trying to understand, measure better, but why? What would you put in the blank there? If you can't measure it, then you can't what? Give me some examples. Yeah. Can't understand it. If you can't measure it, can't characterize it, you can't understand it. I would argue, especially in an academic research environment, understanding is pretty important. What else would you put in there? So if you can't, yeah, Adam? Improve. Yeah, I think that's a really important one. We can't improve, we can't optimize. We can't say we optimized if we don't measure an output, right? Any other thoughts? Yeah. Compare. Yeah. With our last set of experiments, or maybe compare with other labs, or compare with theory, right? We don't know what we're doing. Other thoughts, maybe a little out of the academic research box. I would say that you probably can't scale, you can't manufacture, you can't sell if you can't measure, if you don't know if it meets regulations. So I have a short list here. We've named a bunch of them: improve, optimize, understand. Understanding's pretty key, and reproducibility is pretty key for publishing, and we know that's important. We can't compare, apply, use, regulate, scale, sell, make money off of, etc. But the really fun thing about characterization is it often leads us to new research ideas as well. So again, I have a deep passion for characterization. And I hope that today I can show you that AFM is a really unique, special, powerful, and versatile technique for characterization. We can get a lot from this one technique. And so, of course, we've got imaging with sub-nanometer resolution, measuring forces between surfaces in the range of piconewtons. There's tons of modes. I'm not going to list them all today, but both for imaging and for measuring forces. We can now do fast scanning and fast imaging to get information in real time. That's something that our AFM can do, so we can look at crystallization of materials. Our samples can be in air, vacuum, in fluid environments at a range of temperatures and humidities. So we have a heating stage, you can get hot stages, humidity controllers. We also have a small tensile device that goes in the AFM, so you can pull on it and do mechanical testing and imaging at the same time. But we would say that generally, you don't have to coat your samples, so the sample preparation is pretty straightforward, and the operating costs are really low. Okay, so super versatile, and I'll try and give you some examples today, but really I just want to get you thinking, what can you do with AFM? And so for those that are curious, I'm Canadian. I'm born on the very east coast of Canada, and I've been sort of making my way across the country slowly. But I did all my degrees at McGill in Montreal in chemistry, really fell in love with AFM towards the end. And then I went to Sweden to KTH, Royal Institute of Technology in Stockholm, to focus more on AFM and surface characterization. So I was working in surface and corrosion science, and then across campus with fiber and polymer technology as well. And so in 2011, I started my own group at McMaster in chemical engineering. And then I was recruited here in 2019 as the President's Excellence Chair in Forest Bioproducts. So this is me with the former university president, if you haven't met him. And my group is called the Sustainable Nanobiocomposites Group. And like Ben said, joint between chemical and biological engineering and wood science and forestry here. And so the reason that I'm telling you this is because actually today I'm going to tell you about research that's done at almost each one of these stages, and that's pretty rare for me. I normally talk about very recent work, but I wanted to pull different AFM examples so it comes from different points in my career, which is kind of fun. So overall, my research is on colloid and interface science with a focus on bio-based materials, biopolymers, and nanocellulose. And so has everyone here heard of nanocellulose? I recognize lots of you, so I think you have. I mean, it's pretty obvious, right? Like really small cellulose. But we don't get nanocellulose by growing tiny, tiny trees. We get nanocellulose by isolating or extracting it from natural cellulose sources. There's lots of cellulose sources, but we tend to work from plants and wood pulp, where we can either mechanically break down cellulose, basically by peeling, and then we get these cellulose nanofibrils here, so really thin, long, a few nanometers in cross-section, more like a spaghetti form of nanocellulose. The other option is to use chemical methods, so acid hydrolysis or oxidation, and this gives us cellulose nanocrystals that are shown in the middle. They're more like whiskers or toothpicks, or nano needles of cellulose, and these ones are highly crystalline. They're polymer crystals, and you can think of them a little bit more as being rice-like, although if we're being specific, I'd say uncooked rice versus cooked spaghetti. Okay, that's the end of my food analogies, but you get the idea. One that's long, thin, and in tangles, and one that's a bit more like a toothpick. And we use these materials to make composites, to make films and coatings. The cellulose nanocrystals in the middle here form liquid crystals and have really interesting optical properties in water. We can make gels and foams and emulsions for a range of applications, and quite often looking at these materials as model systems. So when I say model systems, we want to better understand the interaction between cellulose and water, cellulose and polymers, and that's really important for the pulp and paper industry, for composites, and for textiles in particular. And so we have lots of ideas of what we want to do with these materials. Sometimes we're enhancing already existing products. Sometimes we're enabling entirely new materials. But the real goal is to displace petroleum-based products and plastics with these natural materials that have all sorts of interesting properties. What I really want to highlight here, though, is that the materials aren't new. And so they were imaged by electron microscopy and identified as early as the 1950s. So nanocellulose is not new. What is new is the industrial production of it on ton per day scale. And Canada is really leading the race in industrial production. We have companies from coast to coast that are producing different kinds of nanocellulose. And so now is really the time for this material to be used in commercial bioproducts and applications. So my research program aims to bridge this gap between all the industrial producers of nanocellulose and then the commercial end users. So who's going to actually use it and produce products. And we do this by establishing nanocellulose as a material platform, which really means a lot of characterization. And so what we want to do is tailor the properties of nanocellulose for strategic Canadian industries. And so in particularly, we've worked using nanocellulose in medical applications, in food, in cosmetics, in energy storage and remediation, in paints and coatings, and in water treatment. So that's some examples there. But basically what it comes down to is that almost everything in my lab means we take biomass. A lot of the time it's wood, but it can also be agricultural or marine waste residue. We break it down, we functionalize or activate the surface, and then we build it back up into hopefully interesting structures. But we don't really just want to make a bunch of different structures. We want to develop the design rules so that theoretically we know how to make any kind of structure and material with various kinds of functionality. And from my experience and background, what I'm really trying to do is link particle chemistry to functionality, and AFM turns out to be a really helpful tool to make those connections. So that's sort of where most of the projects fit in that I'm going to talk about today. But to take a quick step back about AFM, atomic force microscopy, the principle is fairly simple. You've got a sharp tip on the end of a cantilever. It's moved with very, very high precision over a surface, and you do that using a piezoelectric scanner. And then there's a laser bounced off the back here and goes into a detector. And so the reflection of the laser off the back of the cantilever tells you that the tip's moving up and down and side to side and allows you to build up a topographical map. So that's your image, right? And there's different ways you can image. You can push hard on the surface or push soft, or you can tap along, or you can barely touch it at all. And those will give you different kinds of images. But again, today I'm not going to focus too much on the imaging. The force part that I've underlined here is that this tip is actually touching the surface. So now we can measure forces, we can measure phase, we can measure how stiff or soft a material is, or we can bring materials together, pull them apart, look at adhesion, look at pre-contact forces. And the way that we know the force is by using Hooke's law. So really simply, the cantilever is a spring. It has a spring constant, and the deflection of the cantilever up, down, times the spring constant gives us a quantitative force. So it's pretty straightforward, but we're measuring forces on the order of piconewtons to nanonewtons. And just for reference, a chemical bond is about 1 to 5 nanonewtons. So we're measuring chemical and physical interactions at interfaces, and that's the basic principle. So just to give one example of AFM imaging, because I know that's what most people are thinking of when they think of AFM, this was imaging that was really, really critical for industry. And so normally you think, oh, we want pretty pictures because it's great to see what we have. In this case, it was part of a benchmarking study where we were looking at commercially available cellulose nanocrystals and really trying to identify their similarities and differences. And I'm not going to go into the long details of the study now, but we were asking ourselves questions like, are the CNCs from the 7 different producers, are they all the same? What are the key base properties? And are these materials clean when you buy them? And in short, we did a lot of characterization side by side, and everything looked pretty similar. So nothing too exciting to think about there. But we could say that all of these industrially produced materials are pretty good, uniform, reproducible. They're made by different processes and from different starting materials, but all in all, pretty similar. Now, where they did differ allowed us to now start to make recommendations. And so we're not saying one cellulose nanocrystal is good and the other is bad, but we're saying if you want the best thermal stability, we know which one. If you want the best optical properties, or if you want the one that's a good rheological modifier, choose this one, choose that one. You see the point. So it wasn't trying to identify the best, but by doing careful side-by-side characterization, it really gave us more insight so that we could link properties to performance and have like a guide for people that want to develop these nanocellulose-based products. And so in doing this, we decided that the 3 key properties that our cellulose nanocrystals need to have in order to say that it's a good CNC is colloidal stability, nanoscale dimensions, and high crystallinity. Again, it's a polymer crystal. All the chains are packed parallel and very ordered, and that gives them interesting electromagnetic and optical properties. But for the purpose of today's presentation, it was needing to know this is really important to the producers. So we said, okay, we can do lots of AFM imaging. And not that these are the prettiest AFM pictures, but you can see there's similarities and differences. Some have little flecks, some have more, less particles. This is just lots of different companies with and without purification. Don't worry too much about the labels. But overall, all the CNCs, had basically the same rod shape. We could calculate the average length by measuring about 150 particles, the average height by, again, measuring 150 particles before and after purification. And then the ratio of length to height gives us the aspect ratio, which is important when we're thinking about reinforcing composites, for example, or trying to make mesh-like materials where you want long and thin particles. So I'll just highlight here for a second that we normally measure the height. So that would mean we draw a line profile across and then we look at the height of the particles, but we don't normally measure the width. Do anyone have an idea why I have a height measurement but not a width measurement here? If you've done AFM, you might know. So one of the disadvantages of AFM is that if what you're measuring and your tip are sort of the same size, then you end up with tip broadening. So the tip's got to go over my particle and everything's going to look fatter than it really is because it's basically the width of the tip plus the particle and then the tip on the other side. So we tend to ignore width measurements, and if we needed them, we'd go to something like transmission electron microscopy and we stick with height and length. Anyway, this is just to say we could do lots of imaging. We measure the particles. The size all looks pretty good. Our shortest ones were the lab made, and the longest ones were from a company called Melodia. They were also great rheological modifiers. But we also go in further that it's not just the dimensions and the size and the appearance, but the size distribution that matters, right? And so sometimes a narrow size distribution will give us better liquid crystalline properties, just as one example. So we saw that the purification didn't change our size distribution, but we did have some that had more small bits and some that had higher, were more enriched with a longer fraction. But just to say that we could do this, but it's done manually, again, measuring 150 particles or so. And after years of doing this, we have all decided that this is a bit tedious and subjective. So I wanted to tell you a tiny bit of something that we're working on now to stop measuring particles by hand. And I can say that I have worked on standards development with Canadian Standards Association and ISO. And so measuring 150 particles by hand is the standard, but I think we can do better. So our current approach is developing an automated analysis workflow where we take our AFM image. We have some very minimal set parameters about what to measure and not to measure and how to flatten the images. This is something that I'm really excited about, that we're doing a tip deconvolution so we can actually figure out what the width is now and the quality of our tip. Was it a good sharp tip or was it a kind of dull one? We figure that out. And then we go through a neural network classification and learning and teaching how to identify what is and what isn't a cellulose nanocrystal. And so you can see we've got some aggregates, some other, and the yellow ones in there are all the good CNCs. And then instantly we have about 1,000 particles measured, and we have all 3 dimensions, the length, the width, and the height. So we can calculate the aspect ratio and other characteristic properties as well. And so just a few examples here of what it's picking up right now. These are the ones we would consider CNCs, some aggregates, and some other. And so we're really happy with this not being nearly as subjective as it used to be. So really objective parameter optimization, fast, thousands of particles, and taking advantage of the width information and the tip quality is now something that we can do. The plots here are actually just showing the comparison between automated versus the manual to show that more or less they line up, but we know that it's really subjective when we measure by hand. And sometimes we set ourselves cutoffs like don't measure anything below 100 nanometers, and whether we should or shouldn't do that is a bit questionable. If I show the automated versus manual histograms, the first thing you notice is there's only a few particles measured manually, but lots and lots of particles that are measured through the automated method. But overall, the median of both the length and the height is the same as what we've had before, but now it saves us a lot of time and becomes a more robust data set. So this is something that a current postdoc in my group is working on, Dr. Kevin Balu. And for people that are interested in image analysis, we'd love to chat with you more. And he'd be really happy to share the code, which is in Python, because he doesn't want to do anything that's stuck with subscription-based MATLAB. The reason this hasn't been done before is because rod-shaped particles are much harder to do automated image analysis on, and these ones are so polydispersed because they're a natural material. So of course, if you have materials with nice shapes and spheres, it's really easy to do this, both automated, writing your own code, stuff that's available for Python. We often use Gwydion for AFM analysis, and ImageJ. So there's lots of options, but not that much for these kind of wacky rod-shaped particles. So I'm pretty happy with what Kevin's working on right now. I wanted to show just one other imaging mode before I jump into forces, and that is modulus mapping. And so again, poking at the surface, we can tell the stiffness. So we can derive a Young's modulus. And in this case, we actually mix the two kinds of cellulose nanocrystals, those are the big dark ones, and then intertwined all through there is some cellulose nanofibrils that are tangled up. And so in the same image, we could come up with the Young's modulus of cellulose nanocrystals and cellulose nanofibrils, and that's using AM/FM imaging. So just one image, modulus of the two different particles. You can also use peak force imaging, which is another way to do modulus imaging. In this case, we have our height image and our modulus image. And in that work, what we were doing was getting the modulus of the individual components, a polymer and a cellulose nanofibril, and then comparing that to doing more conventional tensile tests on the films. And so how do the individual properties compare to the bulk properties? So a few examples of what you can do when your tip is making contact with your surface. Good. Any questions about imaging? Because otherwise I'll go back to forces. And there are beautiful images on the internet that people collect with AFM, and I just showed you some stubby rod-shaped particles. But it wouldn't be my work. So I encourage you to look at the different imaging modes and some of the beautiful art that is made by AFM. But I also caution you that getting really high resolution, beautiful images, it does take time. And in the old days, they said like at least a week of work for one publishable image. AFMs are so much better now that that's not at all true, but still it's not 5 minutes. It's at least an afternoon or maybe refining your sample prep, right? So the force part of AFM. We love having a sharp tip because it gives us high resolution in imaging. But actually having a sharp tip isn't great for forces because you don't always know how sharp your tip is or exactly its size. And contact area is really important when we're deriving forces and comparing to theory. So instead of using the sharp tip, we glue a colloidal particle onto the end of a cantilever. This is normally about 1 to 30 microns in diameter and can really be any kind of material you want. Your data analysis is easier if your particle is rigid and doesn't deform, but you can do bacteria or live cells or squishy things if you want, okay? So the idea here is that now we have a material of interest that we're going to measure forces between, and we have a larger contact area, so we're measuring more forces, we have more resolution, higher signal to noise, higher sensitivity, and this allows us to have measurements that are more reproducible and comparable, both when you change your probe or to what other people have done in the literature, or if we want to normalize our data and compare to theory, we basically need to work in this colloidal probe method. If you stick with a tip, you need to do all your measurements with the same tip. And if that tip breaks halfway through your experiments, you have to start all over again. But here, if I have a sphere and I know its radius, I can break it and start with a new one and it's still okay. So that's one reason I like it. You can buy colloid probes. Novascan sells them, or you can glue them yourself. And so we have the setup here, and this is something I did a lot during my postdoc / would buy other people lunch if they would glue them for me because I wasn't that good at it. But you basically buy cantilevers that have no tips. You have your particles of interest. It could be, at one point we were doing like milk powder, milk powder, skim milk powder beads, and we were looking at like chocolate interactions. You take tungsten wire that you've etched to be really sharp, and you basically pick up these particles and stick them onto the cantilever using epoxy, either a dual component epoxy or like a heated epoxy. You can do it under a microscope, and this is just a micro manipulator, like a joystick for moving things around carefully. And some people glue them in the AFM as well. So that you could do that, but it takes a little bit of time. Just to say that the options are endless for whatever you have a defined material of, you can glue it onto the end of a cantilever. And so now we're trying to measure these colloidal forces, which we know are the forces that govern everyday processes like biological systems, our environment, and are really important for material design, things like paints, composites, paper, soil, again, biological. But the short answer here is that when you have very small particles that have a high surface area to mass ratio, it's the intersurface forces that matter. Gravity does not play an important role. And so these are the forces we need to characterize to know whether something is going to be stable or unstable. And so there's lots of different kinds of colloidal forces we can measure: short range, long range, those that are present at all ranges. When we're talking about solid particles in liquids, we can infer hydrophobic and hydrophilic interactions, steric forces, solvation forces. So this is showing basically ordered solvent molecules as you push through with a probe. If we've got polymers, there's polymer bridging, depletion forces. There's lots of options, which can make data interpretation very interesting. But the typical theory that we turn to when we're talking about particles in a liquid environment is called DLVO theory. And so DLVO theory is very simply the sum of electrostatic double layer repulsion. So the repulsion here, when we try and bring two charged particles together, they repel each other, but there's always van der Waals attraction that's present. So this is a negative force is an attraction, a positive force is a repulsion. And the combination of van der Waals attraction and electrostatic double layer repulsion adds up to DLVO theory. And DLVO stands for four guys' names: Yagin, Landau, Verwey, and Overbeek, but everyone just calls it DLVO theory. But the idea here is that this sum, so now this solid line here, basically tells you whether these two particles are going to agglomerate or aggregate, and is it going to be reversible or irreversible, or are they going to stay happy and suspended in solution? And the idea is that particles can access a much smaller space in the diagram, and so they get trapped much more easily than molecules that can come together and come apart really easily. Particles don't. They get too close, van der Waals take over, and they stick together. So this DLVO theory is most often what we're comparing our AFM measurements to when we bring two things together. Once they're together, then we're measuring adhesion. How hard is it to separate them? But approach force curves, we normally look at DLVO theory. So I just wanted to mention that one quickly. So I'll show you what we do when we do an AFM measurement. This is the deflection of the cantilever versus the distance. So we start out far. Our probe is up here, our surface is down here, and there's no interaction. So we start out with no deflection. This is my 0 line. But as I bring the probe closer to the surface, let's say they have an attraction, and so an attraction goes below 0, and my deflection drops down until my probe is touching the surface, and then I keep pushing, and now my probe and my surface are basically just moving together. I've made contact. Okay, now I can go and I can retract from the surface with my probe, so I follow back along the same line. But if those two materials like to stick to each other and I have adhesion, then I'll back up a little bit further until it actually lets go. And so we call this a pull-off force, or the area under the curve would be the adhesion energy. And then we're back to no deflection once it lets go. So that's what we're doing in a force curve, starting far, coming in, and going back out. But now we need to take this deflection distance data and we need to turn it into a force curve, the ones that we will compare to theory and that we'll show in the publications. And so what we do is we take these two linear zones here and find their intersection, and that's where the probe and the surface touch. So that's our 0 point. We now have a 0 point that we can define. And then another important thing from the force curve here is the optical sensitivity. So this is telling us how moving our cantilever or our sample with nanometer precision, how that translates to the signal in the detector. So it basically tells us how movement is reflected or how movement is detected by the photodiode detector. So we use this sensitivity and this 0 point, and now we have what we normally call a force curve. So force in newtons and separation, where this is the 0 point. So that's what most of our curves look like going forward. Okay. So one example from some of the first force curves that I ever made was measuring a silica probe against a polymer nanocellulose composite film, and this was done in sodium chloride solution. And so this is a force curve, again, force versus separation. And what you see here is that these anionic probe and an anionic surface, they repel each other. But as I add more salt, that repulsion is screened. So instead of the repulsion being the one in red, the blue and the black are a screened repulsion. And then the solid and dotted lines there are fitting that to theory, showing that this matches DLVO theory of two charged surfaces approaching each other. But that's the case at pH 5.5, where all the surfaces are charged. If I drop the pH to 3.5, my anionic surfaces start to lose their charge, and my cationic surfaces, or polymer in this case, is much more charged, and I see a completely different force profile. So now, as I come together, I'm actually seeing an attraction, and it's an attraction that's salt dependent, which is attributed to polymer bridging. So my composite swells, and the cationic polymer reaches out and interacts with the probe selectively. So what we can see is the effect of salt and the effect of pH on the interactions, and we can see how that actually affects the DLVO theory as well. And so these are films that are responsive and interact selectively with an opposing surface, just as an example of measuring these pre-contact surface forces. So then the other forces that we're interested are friction. And so friction is just the force resisting the relative motion, so materials sliding against each other. And when we're doing this by AFM, we're going to look at how the cantilever twists. So we're looking at the torsion. So what I showed before was looking at a deflection down or a deflection up. Now we're going to look at this torsional twist of the cantilever. And we're going to bring our probe in contact with the surface and slide side to side and look at how it turns or twists. And we can push hard or we can push soft. And so that's the normal load, how hard we're pushing down, and then the relative motion, and the motion that's causing this to twist is the friction force. So I'm just measuring the twist from friction, and then we always calculate the friction coefficient as well, which is how the change in friction changes with the change in load. So how hard I push, how does that affect the friction, a lot or a little? That's the friction coefficient, okay? And so adhesion and friction are going to be really, really sensitive to the contact area. Again, this is a good reason to have these colloidal probes instead of a sharp tip that's not as well defined. Then in that contact area, there's the chemistry and the forces, where we've got lots of options of things that can be going on between those surfaces. But there's also geometric constraints in terms of the actual molecular contact, or maybe mechanical interlocking, how things get stuck together. And then capillarity. So capillary forces, if you have this kind of surface, you bring a probe and a surface together, and you have just a little bit of a water meniscus that will always form, that really holds those things together. So adhesion will be high, friction will be high. It's hard to separate those materials. So sometimes we want to measure this, but if we want to avoid this, we just submerge the whole thing in liquid, and then that gets rid of a meniscus and the effective capillary forces. So an example of looking at both forces and friction in the same system is this one, where we actually glued hair onto the end of the cantilever. So a piece of hair, and then gave it a free ion beam haircut to cut it off at the ends. So a little piece of hair in one direction and another hair glued down onto the substrate. And now we can measure hair-hair interactions. And we looked at bleached hair versus normal hair, and did that in cationic surfactants, shampoo, and looked at friction as well. And so we learned quite a lot about the forces as you bring things together. It's two charged pieces of hair. They repel each other. That repulsion follows DLVO theory. So that means if you put lots of surfactant or shampoo in there, it screens the repulsion and there's not as much. But also in the case of the bleached hair, where you now have these lipid layers that are exposed on the external surface of the hair, we were able to calculate the surface potential. So this is the surface potential of bleached hair, which you can calculate by doing these force curves. And there's not really another easy way to measure the surface potential of a piece of hair. And then when we look at the friction measurements, this is going from root to tip and from tip to root, with these big bumps being every time the cuticles sort of hit each other. And so you could really understand the structure and the friction and the interactions between hair as another example. So now I'm going to jump into a slightly longer example that has nothing to do with cellulose or natural materials. But this is one that I worked on as a postdoc, is looking at ionic liquids as lubricants. And so in this case, we had probes made of silica and alumina, surfaces that were silica, Teflon, or mica, and then the whole thing is immersed in an ionic liquid. And what we were trying to get around here is the stiction and wear that ruins miniaturized devices. So things like NEMS and MEMS, in air, the capillary forces basically take over and everything gets stuck. And so, sure, we can use conventional lubricants, but most of them have some disadvantages. And so the thought was, can we use ionic liquids as lubricants for these small devices? And we think that using these molten salts that are sort of greener and considered non-toxic will work well, because they are not volatile, so they're not evaporating over time. They have really good thermal stability, conductivity, and they're highly durable, so they can handle this kind of friction and rubbing of mechanical parts next to each other. But for those that aren't familiar with ionic liquids, they are exactly that. They are not a salt solution. They are just ions, but ions that don't pack very well so that they stay molten or liquid at room temperature. So we used ethyl ammonium nitrate. So this is the ethyl ammonium cation and the nitrate anion. And essentially, they're sort of bulky and they don't pack well like NaCl does. So at room temperature, it's a liquid, an entirely ionic environment that is a liquid of ions that flow past each other. Okay, so we immerse our whole system in this. This is a really well-studied ionic liquid. And in short, the friction force from air to ionic liquid for all the material combinations is pretty impressive. So ethyl ammonium nitrate, ionic liquid friction, very, very low. Looking at the friction coefficient, so how sensitive is friction to the load. Again, you can see that in almost all cases in ethyl ammonium nitrate, the friction coefficient is almost identical. So it tells us that the friction and the friction coefficients are really low in ionic liquids. The properties we see are in fact better than in water and similar conventional lubricants, and it's not very dependent on the chemistry of the surfaces. So the ionic media basically gets rid of any other intermolecular forces happening in between alumina and silica, or with Teflon, for example. But so sticking with this ionic liquid, it was well known in literature at the time that this ionic liquid structures at surfaces. And it goes from being really ordered near the surface to less ordered far away. And so this kind of structure of anions and cations in the ionic liquid had been measured by neutron reflectivity, for example. And we thought if we come in slow enough with our AFM probe out here and we approach the surface slow enough, maybe we can see this. And so I'm going to show you that if this is my cartoon here, a mica surface with ordered liquid molecules around a probe, around a surface, that as I approach that probe to the surface, I can actually see the layers squishing out. Okay, so this is now what the force curve looks like. So force versus separation. And what I do here is I bring the probe down and I pop out one anion-cation pair at a time. So I've got 4 jumps in my curve, 1, 2, 3, 4, where the probe jumps in and squishes out a layer of liquid. So I can actually measure structure in the liquid in the force curve, and then the last little jump is a little bit smaller because it's only knocking out one, not an ion pair, but just the cation. So I can see this structure in my force curve because of the discontinuities. And then if I take this force curve and I flip it, rotate it 90 degrees, I can use it to try to understand friction a little bit better. Okay, so this is the same force curve I showed on the last slide, but now I have separation on the x and force on the y, and essentially my friction as a function of normal forces, how hard I push and then slide. And what we see is that we have 3 different regimes of friction. We have one where there's lots of ionic liquid between the probe and the surface and everything slides really easily. That's my first regime. Then I have one where I've squished through a whole bunch of the layers and I have just a little bit of ionic liquid left. And that's the second regime here that's really sensitive to how fast my probe is sliding. And so the friction coefficient, you can see, is dependent on the speed that I measure at. And then I go back into this third regime, which all of a sudden doesn't depend on sliding speed and is basically just having one molecular layer. So like a little ball-bearing molecular layer of cations at the surface where I have, again, very, very low friction coefficients for the system. So the numbers and the exact conclusions here aren't as important, but the idea that we can correlate normal forces to friction forces is pretty interesting, in that you could actually measure friction at different spacings, so close to the surface and far from the surface. So we think that ionic liquids work pretty well as lubricants in this system, and that the nanoscale friction in this case was really dependent on the structure of the ionic liquid at the surface, and then a little bit on the surface roughness, but didn't matter what the chemistry was of our surfaces. So the AFM was helpful for understanding this system a little bit more. The next example is heading back to nanocellulose. In this case, nanocellulose with surfactants. And so I've already told you that cellulose nanocrystals are these rigid toothpick particles. They're great at stabilizing interfaces. So oil-water interfaces, air-water interfaces, they make like a mesh, and you don't need very many, and they really stabilize and make for great, strong interfaces. And so in a number of examples, we were combining cellulose nanocrystals with surfactants that would stick to the surface, and then we would add oil or monomer and sonicate to make a nice dispersion where we have these liquid droplets with cellulose at the interface. Okay? And so these kinds of emulsions are used everywhere in food and cosmetic, pharmaceutical, and household products. But if the oil is actually a monomer, we can polymerize it. And so you polymerize it, you make a polymer, or what's called a synthetic latex. And so then those ones are used in paints and coatings, adhesives, toners, and rubbers. And we've been particularly interested in making adhesives, so pressure-sensitive adhesives. So we know that we can use cellulose nanocrystals to control our emulsions, to either have, sorry, I know the resolution is not great here. So green inside, water and oil emulsions, green outside, meaning we have an oil and water emulsion, or we can make these latexes where the cellulose is floating around in the water phase, or where the cellulose is at the interface, or where we actually put the cellulose particles inside the polymer latex particles. So we have a lot of control. But what we really wanted to know is the interaction between the cellulose and the surfactants. So in this case, we went back to AFM to do some force measurements. Now we have a cellulose film and a probe, and the whole thing is immersed in surfactant. So a cationic surfactant with an anionic probe and an anionic surface. And we want to know, what is the surfactant doing? How is it binding or adsorbing to the interface? And so in our force curves here, again, probe, surface, you're approaching, and we have this big bump. And this bump here is exactly the size of a micelle. So we know that we have a bunch of surfactant micelles that are adsorbing and sitting along the surface. And that's in the case where we have a cellulose nanocrystal film where the anionic charge has a proton as the counter ion. But if I have a sodium as the counter ion, which screens some of the surface charge, I don't have the same structures. I actually end up having bilayer structures of surfactants at the surface. And this one's really easy to press through. So I can squish through it easily with the probe because you see the force is like 0.2, whereas here I'm up more than an order of magnitude higher. So this is a structure that's tightly absorbed, well ordered, and hard to remove. And this is a sort of squishy layer that's pretty easy to push off using the AFM. And then on the flip side, if I take a non-ionic surfactant, my force curve shows me nothing, meaning that that surfactant doesn't absorb or bind at that interface and therefore doesn't control the properties. So that's an example with cellulose and surfactants. Now I'm going to tell you a tiny bit about these latex-based adhesives because this has been a really fun project over a few years. And at this stage, BASF has scaled up the adhesives to pretty large scales. So the idea is we're trying to make these adhesives that are used in tapes and labels and Post-it notes. They're the sticky ones that you want to stick really well to the wall, but when you remove it, it doesn't leave sticky stuff behind, right? So that means we're trying to design an adhesive that is both cohesive, sticks to itself, and adhesive, sticks to the opposing surface. And so the first thing that we did is develop a protocol for making the emulsion polymer latex that has cellulose nanocrystals in it without the polymerization coagulating, because when it does, in this 1 liter reactor, you get a very, very sticky mess and everything sticks together and it is all sticky and horrible and you have to clean it for a day and start again. So the first thing we did was figure out how to make the adhesive without everything sticking together. Then you basically have water with polymer particles and CNCs, and you cast it into a film on a backing material. And so in this case, onto a plastic material. And then you do the standard tapes and adhesives measurements, which is a tack test, meaning a loop that comes in and measures initial stickiness with the surface, and peel, so peeling it off. So these two things here are adhesive properties. And then we do a shear test where you stick your adhesive to a metal plate and hang a weight and wait to see how long it drops. And that's testing how well the adhesive sticks to itself. So adhesive properties, cohesive properties. And to make a long story short, all the properties improve when we put cellulose nanocrystals in there. So tack and peel and shear, they all go up as we add cellulose. So that's great for us. The shear, the cohesive, goes up a lot, like 20-fold, and the tack and peel pretty good. And this is really, really uncommon. Normally, when you add something to try to make adhesives stickier, they become less cohesive and vice versa. So one additive that improves both properties was pretty exciting. And there's also low loadings, which meant it was a cheap additive for our industrial partners to move forward with. And we've seen this behavior across lots of different monomers and polymers and with different kinds of cellulose nanocrystals, essentially where these top ones here are commercially available. So that was good to move forward. But honestly, we didn't know why. And I kept saying, why is this happening? And they kept saying, look at the data, it's happening. And like, I know, but why? I'm like, oh, because it's improving it. And this shouldn't happen, but it does. Okay. But so I was like, but I think we can probably use AFM to understand really what's going on. And like, why is one kind of nanoparticle improving cohesion and adhesion? And so in that case, we used AFM imaging to look at film coalescence. That means you've got all these little latex polymer particles. They need to come together and like coalesce, melt into one continuous network. And when they do that, you get a good film and a good adhesive. So we could look at the onset of film coalescence using AFM. We could look, I know you can't see it from the back there, but there's all little CNCs sort of bridging the spheres together here. And so that was bringing everything together and holding the films together. That's why my cohesive properties and the shear measurements are so good. So in one sense, the CNCs improve latex coalescence, so you get better films and they're tethered to the polymer. But then to measure the adhesion, we went to force curves. Everything's below 0, so this is attractive adhesive forces. And in short, as you add more CNCs, you get more adhesion because the nanoparticles act like anchoring points and the polymers get tangled around and holds everything together. So we could really use AFM to explore this a little bit further rather than just saying, yeah, they work. Okay, and so my last example here, just for the last few minutes, is looking at some food packaging. And this work was done by a visiting PhD student, Juliana, who came from Brazil, from University Federal de San Carlos. And she was making this multi-layer packaging, all made of bio-based materials. The bottom layer was carboxymethyl cellulose, so a nice film-forming transparent polymer. Then she put a protein layer with casein on top. This is like a laminated film on top. This has a water barrier layer in the middle. And then they spray coat on top another protein layer of Zyne. So 2 proteins, 1 polymer, and a 3-layer film, which actually works really well, has great oxygen and moisture barrier properties, and theoretically is edible if you want to. But so she wanted to better understand the interface between these different materials. And so we went to do colloid probe AFM, where the probe was modified with protein. We attached a bunch of casein protein onto the probe, and then we looked at it with the top interface and with the bottom interface in order to understand the interaction forces between layers. And so to get a whole bunch of force curves, she did this mapping where she basically just took force curves all across her packaging, right? Like all sorts of it. And then they all just get compiled into an overlaid, a whole bunch of force curves. Okay. So if you look at this from AFM imaging, this is really big, 100 microns, but that's because her probe was like 10 microns big. So it's like taking an image with no resolution is essentially what this is, because you have a big fat probe. But it's a fast way to go across a large area, get a bunch of adhesion curves, and then plot them in a histogram. So that's what we're doing there. And in short, not to go over all of the results here, but if we look at the protein interactions between casein and Zyne, you can see that the adhesion forces are reasonable. And if I leave my probe in contact with the surface longer, the adhesion goes up. So if I come and I wait, the adhesion increases from 2 to 8. Okay. On the flip side, when I look down here at my protein versus carboxymethyl cellulose now, the adhesion is much lower. So these two things don't interact and they don't adhere to each other. So we added a compatibilizer, which in this case was tannic acid and worked like a crosslinker, a bit of crosslinker, a lot of crosslinker. And what that did is it increased the adhesion. So it increased the adhesion by adding a compatibilizer, and the compatibilizer plus leaving them in contact for a few seconds made for a really, really good interface. So the protein-protein interface on its own was pretty good. The protein-polymer interface, not as good, but by the time we left them in contact and added some tannic acid, we could get interfacial cross-linking at the interface. And so the idea here is that we did these nanoscale measurements of the interlayer forces, but then we compared them to macroscopic, like peeling delamination, contact angle, and oxygen barrier. And we can see that what we measured by AFM correlates with the macroscopic properties as well. And so with that, I just wanted to say that I hope I've given you ideas of stuff you can do with AFM, lots of nice imaging. So I took some from the website to show you other people's beautiful images. This is our AFM system, again, in the basement of the forestry building. You are most welcome. It's good for all sorts of materials, and I really believe that this is an incredibly versatile technique. And so with that, I want to thank Ben and Joey for the invitation and coordination, and to thank all of you for being here, as well as the students and collaborators that did a lot of this work. Thanks very much.
Thank you very much for the fantastic talk. Do we have any questions?